RC clock source you can use. And the internal RC clock is similar external RC clock, but the things is built inside microcontroller. Okay. So all the microcontroller you bought from manufacturing, default clock resource setup is internal RC clock. That means you turn on the power, even you not have any external clock, your microcontroller still can program, can work, just because the default setup is internal RC clock. This internal RC clock, they have a very low accuracy too, as I said. It's the RC, doesn't really matter what is the internal or internal RC clock. Their problem is low accuracy. And the internal RC clock, the maximum speed can go up to the 8 megahertz. But all the microcontroller by default setup internal clock is 1 megahertz. Okay, you got to remember that. You can change the internal clock speed by setting the field speed, which is the register. You can change the internal clock, internal RC clock speed. But you got to remember the default is 1 megahertz. That is a lot of people, when you first time program the microcontroller, they said something wrong. I want this LED flashing every 500 milliseconds. It looks like every 5 seconds they're flashing. The more slow. Because you reckon the microcontroller internal RC clock is 8 megahertz. But if you not change the field speed, which is the register to change the internal RC clock, default setup is 1 megahertz. You want them to go fast, you need to reprogram the field speed, which is everybody in this class have to do. Right? All the program from second project or last project, we're all going to use the internal RC clock because we are not going to deal with some very accuracy things. Okay, we're not going to use the microcontroller to talk with the SPI, XCOC, or UR. We not use the microcontroller, set up the timer. So we can use a low accuracy clock. But the trouble is you gotta make sure your internal RC clock is set up the speed you want, which is you want 8 megahertz instead 1 megahertz. If you not program the field speeds, you're going to have this problem. And how to program the field speeds, I'm going to talk about those things in the next lecture. Okay, that's next one.
Field speeds.
Because external RC or internal RC, the clock, they all have the disadvantage is very low accuracy. So now we talk about, we're going to use external resonator. This external resonator, their accuracy is better than the RC clock. And if you look at it, that is the symbol for the external resonator. They need the capacitor, so they have the two different resonators. One is come with 2 pins. If the 2 pins, you still need this capacitor. You need to put the external capacitor to make this external resonators work. But you also can buy the 3 pins, the external resonator. Then you don't need the actual capacitors to make this clock work. So that depends on what sort of resonator you're going to buy. Okay? That's 2 pin and 3 pin. 3 pin will not need this capacitor. 2 pin, you don't need it.
Same price or different price?
Different price. Definitely this one will be more expensive. But good thing is you put the 2 capacitor and take your space. And that is how you put the external resonators on the microcontroller. You can see that is the power pin we talk about, right? And you put the central pin, and which is between on the two capacitor put on the ground, and another two pin you link to the clock pin on the microcontroller drop down. So that is the external resonator. Look at this microcontroller PCB. You can see that's the microcontroller. That is the external resonator. When you lay out the PCB, you gotta be careful. Anything is clock, deal with clock. That means they're going to create the noise because without clock, go turn on, charge, discharge. They got the pulse, and the pulse can go 8 megahertz long. If you select 16 megahertz, the clock microcontroller, then the clock can go 16 megahertz, and someone can go 20 megahertz. That is very fast. It's on, off. It's 01, 01, 01 all the time. That's very noise, right? So you don't want this clock too far away to your microcontroller clock pin. If you leave it too far away, that means you're going to burn this noise all around your microcontroller board. So if you are designing microcontroller board, you got to be very careful. The first thing, you got to look at the power pin. You need decoupling capacitor, and all decoupling capacitors need very close to the reprinting pins. Second thing you need, if you want to use the external clock, you got to remember they are noise. So you need to put them as close as possible to their clock pins. Yeah. And if your microcontroller also have some ADC line, you need to leave it far away. You don't want this noise to get on your ADC. Otherwise, this noise fitting ADC, you do not your sample together like is the noise or the real sample. So that is very important. So it's got to remember, right? To design the microcontroller, also you got to remember this. External crystal. External crystal, the gate price getting higher, but good thing you look at the accuracy. The accuracy is increased to go up. They are 10 to 1000 ppm. ppm is mean part per millifault. Also that means every million pulse you only got about 10 to 1000 fold. Okay? So depend how accuracy crystal you want to buy. Of course, the more accuracy, the cost more. That's very simple. And the external crystal need external capacitors. Right? So that's things. If your microcontroller deal with like UART program, you need to talk to another device, then you better to use the crystals. Otherwise, like when you send it to talk to another device, if the clock wrong, you could have lost some very important information. And that is the crystal's electrical symbol. A little bit similar like the external resonators. But you gotta remember crystal do need two capacitors put in the system to make this crystal working properly. Yeah, it's just like another way we put a load for the crystals. Otherwise, crystal wouldn't isolation.
How much is it on the old one, the videos? Like how much is $3 that one, $2?
That depend accuracy. That's a back to the accuracy. And then you can buy $3 for buying the crystal, but the accuracy probably 500 to $1. But you pay like $12, you can buy for 10 or 15. Same thing, right? Crystal have
Like my
very
last
close
morning when that's been.
a mic controller of clock pins.
You always used to watch
because
on
they
one
have
speed.
noise parts.
You always watch it one speed.
No, I watch it 1.5.
I watch 1.7.
And
Yeah, all the time.
I have this chart about what difference between the crystal and the resonator. If you're interested, you can read them. Okay? You can see, and this is tolerance is very less for crystal. Resonator's tolerance is high. That's meaning that when you both getting shock and you know, it's depends on which area you're going to use your PCB. And if you go through those things, you can decide what sort of the cloud resources you need to for your microcontroller system. External cloud. External cloud is like IC. Okay, so that's just like IC. They need a power pin. They need power. Now you can feed this clock. That's output. You can feed this clock to your microcontroller, one of XTAL1 or XTAL pin 2. You put one of that pins, you can get clock. This clock got very, very high accuracy, but it's, of course, they getting more expensive. So we talk about the microcontroller, the power clock sequencing is the debugging of the flash port. Why we use the port 4? We already said this. Microcontroller needs to talk with the PC, so you can write the program in your compiler. When you finish, then you can send your program to the microcontroller. The microcontroller do the software want them to do.
Yeah.
So that is reason we need a flash or debugging port for the microcontroller. The microcontroller normally have the three, the communication port or flashing port. One called the ISP, one the JTAG, third one debugging wire. That's a very common one. Okay, basically doesn't matter which manufacturing microcontroller, they basically all have these functions. What different? What is different? ISP is then we said you can just sending the code to your microcontroller and put this code in their flash memory. And this ISP port have the three signal ports. MISO for the master input, the slave output, or MOSI. You already designed your signal project. Then you know you do have MISO, MOSI, and ICT. So this three ports you need to talk with your microcontroller. But not just these three, also need VCC, receive, and ground. Okay, so actually ISP need 6 ports at least. You can talk with microcontroller. So microcontroller, if you look at microcontroller, got MISO pin, MOSI pin, ICK pin. That means this microcontroller is got ISP communication of the flash port. ISP port normally designed for low-level microcontroller. They cannot do the debugging. What is debugging? Debugging is very useful tool. We can set up the breakpoint on your software. We can move my software run to the breakpoint. They can stop. Then I can do the troubleshooting for your software. It's a very, very handy tool for the debugging. That when you troubleshooting your software without debugging, if your software is very complex, you just don't know what's going to do. So we set up breakpoint. Now I know this software stop that breakpoint. Now I know software working. If you set up breakpoint, your software cannot get a breakpoint. That means your software doing some funny looping things before that breakpoint. Now you know you can make your troubleshooting, the fault find area getting smaller. If you have about like 20, 30, even 100 pages of your software coding, without breakpoint, if your software doesn't work, you just don't know what will work. Set up breakpoint, you can easily to minimize the errors on your code. So that is very important. But the ISP, I said, is designed for the low level of the microcontroller. If you see all this pins on the microcontroller. That means this microcontroller got ISP flash port. And that is the port we are using for the program of the microcontroller. And then you already know in the project 2, in the project 3, we're going to use this Voxy connector to link with the microcontroller, the SP port. And your PC run the Atmel Studio, which is a compiler. You write your C program in. When you finish, then you use the USB connector to connect this AVR Dragon, which we call the emulator. Okay? And this emulator have the port, the cable. You plug cable on it, then you can see that is the Dragon board, that's the microcontroller board. Then you can, through this cable, to talk with this emulator, and this emulator through the USB cable to talk to your PC, then you can transfer your code to the microcontroller. That's how it works. Okay, so gotta remember, from this week, you need to borrow the AVR Dragon emulator from me. Alright, so in this course, you need to borrow two things from me. One is the Dragon emulator, then you can transfer your program to the microcontroller. Second one is power bank to power up your robot. The two things you will borrow from me. Alright. From this week, if you got time, you come to see me. I can lend this Dragon board to you. Then once we get into program, you can do the program at home, because this Atmel Studio 7 is a free software you can install on this computer. So once you got your board, then you got your power supply and turn on your project 2, then you can just at home do the program. And how to borrow the Dragon and the power bank, and then you need your student ID. And also, before you come to see me, you need to log in the AUT to the CESO. You need to log in this website first. Okay? Otherwise, you come to see me. If you're not logged in before, the system going to say cannot find you. So you need to go there and log in to put your student ID in the system. The system know who you are. Like you come to see me, when I scan your student ID, I can lend this Dragon and the power bank to you, that you can finish your project. Right? Remember, everybody need it. Don't leave to last minute.
You said Dragon and power bank.
No problem.
As we keep going.
No. He's just saying that we need to log in for that. Remember when I'm
Yeah,
fresh?
I know what you're saying. We need to borrow two things. This and the power bank. What is it? Power.
That's just a simple.
No, we have to borrow these two. The microcontroller and the AVR Dragon.
Oh, the way you say power. Did you hear him say power?
No?
Did he say
Dragon, these ones.
maybe a dragon also?
Huh? That one's AT, yeah. Microcontroller.
JTAG. Next one, JTAG. JTAG is designed for the middle range of microcontroller. The function is similar as SP, but the two things. Use the JTAG, you can do the debugging on the software. And the JTAG have a 4 signal pins: TCK, TMS, TDI, TDO. If you see any microcontroller got these pins, that means their flash port is a JTAG. If you do the final year project, I suggest you to use something like have a JTAG. But depends, if you're doing a lot of programming, then you better use something with JTAG, have the JTAG function. And then they need a power, ground, and the setup pins too. Take a look, this is my controller. If they have all those pins, TCK pins, that's been their flash port is JTAG. JTAG port is similar the SP port we use, which is we are going to use the different we see a different the emulator, we call it the ICE. So that's almost people doing the final year project use this instead of the Dragon's chip, Dragon's chip. And but like I said, it's case by case. If you not design very complex software, very simple driver, you still can use ISP. Yeah, ISP flash port. Same thing. One, because USB port connect to your PC, then through this cable, they can transfer the C language or C software to your microcontroller. JTAG, we're going to use that's normal JTAG. That's the AVR Dragon. Okay, and some people say that the AVR Dragon is different than the AUT one because we put the protect circuits on it. Otherwise, before we just landed this Dragon to the student, what's fun is they so easily broken. The reason they call it Dragon, what's the Dragon? Dragon is like really getting like a file they got easily catch the file. That's the reason. If you get power a little bit wrong, this port is broken. That's the reason we put the protection circuits on, just in case the thing broken. Debugging wire, that's last one. I said is the low level Mac controller normally they use the SP, and the middle level the Mac controller use the JTAG. But in this day, we do want to use the low level Mac controller doing some job, and we also want debugging to sort out the troubleshooting of program. And if they have no JTAG port, all the low level microcontroller normally have the debugging wire can give you the ability to do the debugging. So, and if you want to do the debugging on the low level microcontroller, you need to make sure this microcontroller have a debugging wire port available you can use. Now once you turn on the debugging wire, you can do the troubleshooting on a low level on the microcontroller. The debugging wires only have the one port. They just use the reset up bit on the microcontroller to do the debugging. And how to turn the debugging wires on if you want it, I'm going to show you in the next lectures. You can turn on, you can turn it off, but I'm going to show you how to do it. Well, we're getting very interesting things by output. I is input, O is output. So the microcontrollers, the reason they're really handy, useful, is because they got a lot of I/O port. I/O port is input. If you push button, you can read what is the state of the electronic component, like you push button, switch, that sort of thing. Output, I'm going to drive something. I'm going to drive lights, I'm going to drive the motor, I'm going to drive something else. That is output. So that's input, output different. Don't ask me what is input, what's output. Input, you want to read some information in, almost do like a switch. And output is going to drive something. And the microcontroller, we can see that's one of the microcontrollers at any 4313, a little bit different than the 2313, which is we use on the project 2. The reason different is they have a more I/O pins than the 2313. Because we are project 2, we are using few I/O pins. We don't need complex system. But I just get the electric symbol at 10 2313. We can see they have a lot of I/O pins for this microcontroller. And all this microcontroller is called I/O pin. You can configure to either input or output. They are programmed. All this I/O pin, you see this pin in the direction like this, and you got the two arrows like this. All these I/O pins like that is called I/O pins, bidirection. Okay, so you can program either to the input or output. For example, we look at this I-10231 microcontroller. They are port A have 1, 2, 3 ports, and port B they start from 0, finish at 7, so that's got 8 bits, 8 ports. And port D, they put B0 to B6, so they got 7 ports. Okay, not necessary you have to go with 8 ports. Some port microcontroller is used for the manufacturing. Okay, so that means they take the port 3 off, 3 to 7 off. But 8 port is very normal. Next thing is, let me take a look. All this microcontroller I/O port, the default is configured as tri-state. What is tri-state? Tri-state is mean that I/O port is high impedance. So the resistance value is very high. Why all the I/O port default set up configured as tri-state? Because if I configure this port to the output, I can easily to set up this port to go high or low and use very, very less current to change their state. That is the reason. The default microcontroller I/O port configured as tri-state. Very, very low. And we take a look this circuit over here, right? This circuit over there. For example, if I have got a microcontroller and they have the I/O port to PA0, I'm going to use this PA0 as an input. I can read this button state. Right? So that means if my button push down, this PA0 going to go to the ground. But if this PA0, this button is not pushed down, it's nothing connect to PA0, we call this pin is floating. Right? Because you can see it's nothing connect this point here. There is as tri-state. They have a disadvantage for that. Simple, they have disadvantage for that. Like I said, is because they are tri-state and high impedance, so a little bit of noise, you can change the PA0, either go high or go low. What has happened is, if you have an electronic circuit sit there, and the input pin is floating, they're going to have the problem. What's the problem could be happening is, for example, if I'm going to use this push button, can turn on my big motor on the side to drive something. Right? And if we stand from our PCB, somebody say, oh, this circuit, this part not working. If by accident his finger just touched the PCB, a little bit the static, you change this whole state. If it go low, for example, if it go lower, now you can see that motor over there start. if somebody just doing service on that motor, it could make big mess. Just remember, all the microcontroller input pin, you cannot leave as floating. Because all the static or anything, you so easily can change this input state. So do not leave any input pin as floating. That's another thing you got to remember when you design hardware. Otherwise, you're going to have the big problem. Just like I said, if you use this push button to drive the big motor, somebody doing service, then you come here, say, open the board, open the control board, turn around, something touching the board, that motor start working. You're going to kill the people doing service. So that's disadvantage, I say. It cannot you set the input pin as floating. To fix this floating problem, we can either using the pulling up resistance or pulling down resistance. So that is mean if I got a microcontroller, it's PO zeros there, that's a push button, that's why I come to the ground. That's called floating. If they are active going to low, I'm going to put the pulling up resistance over there. So that is mean by accident if I touch this pin, you're not going to change any state of this input pin until you push this button down. But because they are not twisted anymore, this pin holds up on 5 volts. And if I change the circuits like this, I change the circuits like SPA0, and I'm going to use the push button that means if this push button is going to push down, I'm going to be the hard. So now what I do is I put the pulling down resistance on. Okay. If I do that, I'm not going to have the floating control.
How do you decide the staircase? You need 5 K or 100%?
Depends what you want.
You know what he means.
That is when you program. You want this one push button go low or active, or push button go high or active. Depends your designer. You know what you do. Okay? So you can do this. So this is
putting a
pulling
resistor
up,
make a
pulling down resist 4. Okay, just in case once they're floating, that static can make the wrong active for your microcontroller software. Microcontroller also have an internal pulling up resistance. You can see the good things we fix the floating problem. Trouble is we have to use extra electron components, which is a resistor, to pulling either up or down. But microcontroller have an internal pulling up resistor.